Let's turn the complexity of our models up again and talk about polynomial regression. So we've dealt with this constant model where our predictions are just equal to a single number we call beta 0. We then talked about linear models where our prediction is beta 0 plus some number beta 1 multiplied by the value of our feature. We can even make things more complex and add additional terms. For instance, our prediction could be beta 0 plus beta 1 multiplied by the value of our feature plus beta 2 multiplied by the value of our feature squared. We could try something like this. Now let's say this is the data that we're using to train our model. This is our training set. So we have x1 is our feature and y1 is the corresponding label. We have another point where x2 is the feature and y2 is the corresponding label, and we have x3 is the feature and y3 is the corresponding label. So we're going to use these to train our model. Now, if we're doing linear regression, trying to fit to a linear model, then these are the three things that we are saying are true, or that we expect to be roughly true, right? That beta 0 plus beta 1 multiplied by our feature x1 is equal to y1 for our, because y1 is the label that corresponds to the x1 point. Then we have beta 0 plus beta 1 multiplied by x2 is equal to y2. y2 is the label corresponding to our x2 point. And then we have beta 0 plus beta 1 multiplied by x3 is equal to y3. And y3 is the label corresponding to the x3 point. So given our three data points, these are the three equations that we would, that we want to be true. Of course, in reality, our data is not going to be perfectly linear, and it probably won't be the case. This is approximately what we want to be true. And we can represent this using matrix multiplication. And if you're not familiar with this, you should do a refresher on some of the linear algebra concepts, as they'll be important here. So this is how we represent those three equations using matrix multiplication. This here is what we need to call the design matrix. So those ones represent our constant values, and we have another column of our features, and then we have our coefficients, and this is our coefficient vector, beta 0 and beta 1, and we have a vector of our outputs. And the reason we want to start representing in this form is so we can solve for our coefficient vector and find beta 0 and beta 1. Linear regression isn't too bad. We derive some equations that you can use to find beta 0 and beta 1, but as our models get more complex and we have more coefficients to solve for, solving it that way can become a little bit unpractical. So we start using some linear algebra concepts. And that, again, is for our linear model here. What about a quadratic model, where we have a quadratic term? Well, we have three data points again, so we can generate these three equations. All that's different now is we've added a quadratic term and a new coefficient that we call beta 2. So we have beta 2 times x1 squared is added to our first equation. We have beta 2 multiplied by x2 squared is added to our second equation. Then we have beta 2 multiplied by x3 squared is added to our third equation there. So we've just changed the equations to make them quadratic by adding an additional term. And again, we can represent this in matrix form. We have a new column that has all our features squared. And we have a new coefficient in our coefficient vector, beta 2. And this is a quadratic model. What if another thing that might make things more complex, if we had another feature? We've just been dealing with one feature. For instance, age. What if we had another feature? Well, let's call it q. So our first point, we can add a q1. That's going to be the value of q for that data point. And for our second data point, we have q2. And for our third one, we have q3. And this is our training set. So we have another feature that we've added. And we want to incorporate this into the equation. Well, we can just add another column with our q values. Right? So in this sense, this is the form of our model now. Our prediction is beta 0 plus beta 1 multiplied by our x feature, the value of our x feature, plus beta 2 multiplied by the value of our q feature. And for our three data points that we're using to train, we generate this design matrix. Now we want to find beta 0, beta 1, and beta 2. We want to find the coefficient vector. So how can we do that? And also, this is a multiple linear regression because we're using now multiple features to make the prediction. But how can we find our coefficient vector? Well, just to simplify things, let's write it this way. So A is our design matrix, M is our coefficient vector that we want to find, and B, the B vector is just our outputs. This requires some linear algebra proof that you can look into on your own. However, this is the ultimate equation that you come up with. Our coefficient vector is equal to our design matrix, the transpose of our design matrix, multiplied by our design matrix, and all of that is inverted. We find the inverse of it, and then we multiply that by our the transpose of our design matrix, and then multiply that by our output vector. And doing this computation, which can be quite extensive, but often computers do it for us, will give us our what our coefficients should be in our coefficient vector. And the nice thing about this equation is it actually still follows the least squares method. So whatever we get for our coefficients result in the lowest value for our mean square error. And so we can try building all these different models and we can compare them using cross-validation.